Okay, good morning. My name is Prachya. I'm from NECTech. And also good morning to you guys, the audience from home. So today's topic is about transformer-based language models and some of the popular BERT variants. To give you a glimpse about my talk, BERT is a very popular language model, which is a pre-trained model that you can use it for many applications. So that is the basic idea of the BERT. And today I'll be talking about the mechanism and also the internal procedure where the language is processed. And also I'll explain more about the variants of BERT, where you can apply to your own project. Yeah, that's me. My name is Arm from NECTech. Yeah, you can compute my age from the birthday. Anyway, let's forget about it. This is today's topics. Okay, so the outline for the talk is I'll be focusing more on the first two topics, where I'll be explaining how the transformer model works, and I'll interpret a little bit. I'll give you some more interpretation where the transformer model can be you can treat it as a comparable syntax-based machine translation. And then we'll go to the BERT straight away, and also the BERT variants. And that's going to be the conclusion of my talk. I've got about 1.5 hours to finish all of these, although I've got 60 slides. Good luck with that. Let's try it. Okay, so before we get into BERT, let's talk about the internal structure of BERT, which is transformer. The transformer is actually a very simple model. It works as follows. It tries to convert a sequence into another sequence. It's very simple. It's like a electrical transformer where you've got one voltage and then you convert it into another voltage. It's like that. But now in natural language processing, you try to convert a sequence of words or a sequence of text into another sequence of text. You can treat it as a machine translation, for example, like the one you see up there, that is English, and then you translate that into Thai. So these are the comparable sequences that you can make a transformation. The basic idea is very simple. You can treat it as a translation. It translates one sequence into another sequence. Very simple. But why is it revolutionized the deep learning community, especially in natural language processing? It's because it can learn more than traditional deep learning techniques. The first one is the multi-word expressions. It learns automatically how phrases and idioms are formed. And if you use transformer in other applications like image processing, it's going to learn the same thing. If you can spot some collocations of image or some collocations of process signals, you can treat it as idioms, and it can be learned automatically from the data. That is the first pro. The second pro is the distance. I'm not going to say it's a long distance dependency, but it's moderate distance dependency, where you've got two things that must collocate in the same data set. But at the same time, they are quite far apart. It can be learned automatically too. That is transformer. Although it's quite far from each other, it's still learnable. And also, it learns to reorder. If you want to transform one image, for example, one image into another image, sometimes you have to reorder some fragments of the image. Therefore, the transformer can do that too. And that also applies to machine translation, where you've got an idiom and another idiom which collocate. But in translation, you've got to reorder them. You've got to swap the positions, things like that. That can also be learned. And the last one, which is my favorite, conceptualization. It can learn to summarize things automatically. If you have one groups of collocation, that can also be summarized into one single word. For example, it can do that too. That is transformer. However, there are some cons too, which I'll talk a bit about it later. Let's talk about the first one, multiple word expression. Multiple word expression or idioms can be learned automatically using transformer. If I, for example, treat each word or each fragment of image or sound signals with a vector, the transformer will automatically detect the similarity between each word or each fragment. And with the similarity, it learns the multiple word expression automatically. And these vectors can be adjusted along the way as it sees the data. If you feed more data into it, it will adjust the vector accordingly. So it's very, very convenient. You don't have to annotate any collocation anymore. You don't have to do that. It can be learned automatically. That is the first one. And the secret to success right here, it's actually the way you represent the semantics or the meaning of each word with a vector. This is word embedding. We have learned that in about 2016, where the word embedding was published. So at that time, we learned that each word can be represented in a vector space model. That's exactly the model. And here in transformer, it can also be learned automatically. Yeah, the vector of semantics can be adjusted accordingly with respect to the data. That's the first one. The second one, long distance dependency. But here I'm not going to overclaim that. I'm going to say it's moderate distance dependency. So for example, when we look for something like collocations, like look up, ask someone out, or pay for, these are the collocating words. They must co-occur in the text. That can also be learned, although they are far apart. For example, here, the meaning vector of the word paid and for are quite close. They're quite similar. Therefore, this can be learned. If they are similar, they tend to be collocation. Therefore, paid and for is learned as one multiple word expression, although they are far apart. However, if they're too far apart, like these guys, paid and the second for, the second one will be penalized. It means that you put some penalty into the second one because it's too far. It is too far. And this can be learned automatically too, using the transformer. The distance is used for penalizing the collocation. So if it's too far apart, then it will be penalized. The third one is reordering. This can also be learned from transformer, believe it or not, and it's quite convenient. So the basic idea of transformer is that it takes a look at the input as a whole. It looks at the input as a whole, I mean the whole thing, and then it generates one word after another in the result. This is how it works. Take a look. Okay, so you've got an English sentence like your stable financial status, and you want to translate that into Thai. This is how it works. It's going to focus on some of the words in the input. For example, it learns to focus on the word status. And it takes a look at the dictionary, for example. It translates status into that Thai word, so generate one word. Then, once it generates one word, it changes the status, the current state, just like finite state automaton. And then, once it changes state, it now focuses on the input once again, But now the focus has changed. Now it looks at another words like financial, and then it translates to one Thai word. And then it keeps doing that as it follows through this procedure. The attention or the focus changes along the way. As you change the status, it changes the attention or the focus on the input. So it keeps doing that until you've got the whole sentence. Your question may be, how to stop? The answer is, once it gets to the last word and it will choose to generate. One of the choice that would be prominent is the end of string mark. If it comes to the end of string mark, like full stop, then it stops. That's how it works. The transformer works and it learns how to reorder things in the input into the output. That's why the transformer model is used very frequently in machine translation and in automatic text summarization, or ATS. This is why it is so famous, reordering. And the last one, my favorite, conceptualization. It learns automatically how to summarize words into one concept. It can do that, believe it or not. Right here, this is taken from the real example. Stevenson initiated a scheme for building the first locomotive. If you take a look at the third row, initiated a scheme for building. That is conceptualized into one word, invent. That's one word, invent. It learns automatically how to conceptualize words into one concept. It's so intelligent. Sometimes I got scared by transformer because I don't even know how it learns to do that. But anyway, this is the pros. You can think about your application. If you're going to work on reordering or conceptualization, transformer may be your choice. And some of these applications are now, I would say, is known widely that transformers will play an important role. Like machine translation, for example, I always mention that. Automatic text summarization, or ATS, especially abstractive summarization. When I say abstractive, it means that it creates a new document. It just doesn't take fragments and fragments of text and then put them together. No. Abstractive summarization means that you rewrite the whole document as an abstract. It may be completely different, but this can be learned with transformer. Image captioning, for example, can also be learned with transformer. If you've got an image, it learns the fragments of image, like this is the bird, this is the sky, this is the building. And then it generates the caption automatically because it learns this is the bird. So it chooses the word bird. This is building, it chooses the word building. And then it constructs a sentence based on these vocabularies. It's so simple, but in the same time, you need a lot of data to train the transformer. So you can now think about a lot of things. Like you've got an artifact, like historical artifact, and then you try to generate a story based on that artifact. You can learn that with the transformer. Speech recognition can also be learned with transformer now. If you've got a like speech signal, and then you transcribe that into text, it's exactly the same thing. You've got sequence of speech signals, and then you transcribe, you learn the collocations, you learn the multiple word expression, and then you transcribe each word into text. Not only that, you can also work on more fundamental tasks like part of speech tagging. You can also do that. It's very simple. Parsing, you can extract grammatical structure from the input text. You can also do word segmentation. That's simple, right? Word segmentation. But at this time, you don't just do word segmentation. You also correct the words, or you can normalize it. For example, if you have non-standard spelling. You can convert it into a standard spelling before yielding the result. That is a very smart word segmentation module. And the last one, relation extraction. This is my favorite one, but unfortunately, I didn't include that into these slides, okay? Relation extraction is about extracting semantic relatedness of words in the text. So all we know, if you've got a bunch of text, you can extract a knowledge graph automatically using the transformer. It's that simple. Okay. How much time? Okay, I've got 1 hour. Okay, cool. Okay, so now let's explore how it works, okay? I have advertised the transformer model. I've been an advocate, but now I'm going to show the real bizarre devil. Okay, this is the real devil. Okay, when we jump into the transformer model, we have to deal with the first thing, the scale.product attention. If you take a look at the math up there, you've got goosebumps already, right? Goosebumps, konluk, goosebumps. But in Western culture, we say goosebumps over goosebumps. So it's double scary. Okay, but anyway, the scale.product attention is very simple. In a nutshell, it's very, very simple. It's a search engine. The basic idea is the search engine. So you've got a key. Unfortunately, I don't have any stick I can point. Okay, but anyway, so you've got a query or a key, and you want to open the drawer with that key. So that's your key. You want to open the drawer and get something inside. That's exactly how it works. Okay, so you've got a key or a query, and then you map the query with respect to each keyhole. If it match, you open the things out, you open, and then you take the things out. So it works exactly like that. So you put the query, you compare the query with each keyhole, and then you've got the similarity. The similarity is now the weight. So if you've got the weight, you can get the things out and multiply by the weight. So here, once you've got the weight, you get the value out and multiply that with the weight. You can see now that some value is very, very thin, but some of them are very, very thick. It's so opaque, right? Once you've got them, you sum them. That's the result of scale.product attention. You map the similarity of the key with the query, and then you get the result. And then you treat that similarity as a weight. That is a result. So the pentagon is very thick. The plus is very thick. Therefore, you must have the pentagon and the plus up there. It would be very obvious. But if you represent that with mathematics formula, it's going to look like that, which we don't want to focus, okay? I promised to myself last night that I'll try my best to skip the math formula. I'll try to show you the ideas how it works, okay? But if you are interested in math, yeah, you can come to me and talk about it. You'll be amazed. You'll be amazed by the beauty of mathematics. Okay, and now let's take a look at that. If we compare the keyhole with the words, what's going to happen? Okay, suppose I've got a query like look, and each keyhole is a word. What's going to happen? So you measure the similarity of each word and the query. So you've got the word look with a very strong similarity, right? But at the same time, you've got another word too, up. Because the word up collocates with the word look almost all the time. You've got to look something up in the dictionary. That is the collocation. Therefore, the similarity is also very high up there. So if you've got the match words, then you get the values of those words out, and then you sum them. That is weighted average. In terms of mathematics, it's called weighted average. ค่าเฉลี่ยถ่วงน้ำหนัก Okay. And then you get the idea. Now you get the idea. That is one word, one query against all the words, right? What about you compute the similarity of each word against themselves? What's going to happen? It's going to look like this. This is the table. So you begin with Mary, and then you compute the words. You begin with the query, Mary, and then you compute the similarity of each word, of the word Mary with each key. So you've got the first column. You've got the first column, and then you go through to the word look, and then you compute the similarity. You've got the second column, and then you follow through the queries. So that is self-attention or self-similarity. Easy? Self-attention is actually self-similarity. The idea is very simple, but when you look at the math up there, it's another story. Yeah. This is how we read the paper. We need to interpret the math formulas into the real things. And this is how it works. You match with the Mary, and you take a look, and then this, and then word, and then up, things like that. So you're going to get the self-attention. And as you can see right now, the combined results will show you the similarity as well. So you now can see the output for the word looks and the word up are quite close to each other. They're quite close. That's how it learns collocation and multiple word expression. This is how it learns. See, not that difficult if we get rid of the math. Now let's shift our mind out a little bit from the self-attention into machine translation. What's going to happen if we compute the self-attention between the source language and the target language? It's going to look like this. So you've got the query. The query is actually the target language, okay? It's the target language, the language that you want to translate to, okay? So you've got the word Mary, and then you compute the similarity of the word Mary and Mary along the way. And then search, that word is search. And then word, and then this. So you're going to get the alignment attention or alignment similarity. Attention means similarity. It means that. It's just that. Then alignment attention means that you now can extract the similarity between the source language and the target language automatically. If you take a look at the results, combined results, you can now see the different results for each word. That is the representation of the target language. And here is what we want to see. We want to extract the multiple word expressions either in the same language or across the language. That can be learned automatically too. If you put one language, you can extract similarities or idioms. If you put two languages, then you can now have the dictionary. You can extract the dictionary automatically. And the dictionary is called alignment. I'm trying very hard not to run out of time, okay? So that I can give you some coffee break. 10:30, right? 10:30. 10:30. Let's make it 10:30. Okay. So now, what you have seen is just only one mechanism, scale dot product. And that scale dot product is actually called the attention. I would call it attention here, okay? The similarity extractor. But if you use two similarity extractors, what's going to happen? This is very interesting now. If you have one extractor, similarity extractor, you can learn one multiple word expression. If you use two similarity extractors, you can learn two multiple word expressions or two idioms at the same time. And here, when we use more than one similarity extractors, we call it multi-head attention. The multi-head attention means that you have more than one similarity extractors.
แสดงว่านี่เขาพูดเป็นทางการมากเลยฮะ
I can hear everything from the Zoom. Okay. Anyway, right here, if you use two similarity extractors or two attention mechanism, what's going to happen? Right here, in the first one, you learn the idiom up.
งานประชุมวิชาการ
And the second head, it learns Mary Poppins. It's a proper name, Mary Poppins. If you use more than one similarity extractors, you can extract more collocations. Now let's imagine when we use a transformer for image processing. If you use just only one head, you can extract one fragment. If you use two heads, you can extract two at the same time. So it really depends on your application. If you want to focus on, let's say, 8 fragments in the image, and then you limit yourself with the number 8, then you use 8 heads.
Meeting setting.
That's how we say multi-head attention learns multiple word expressions. One head, one fragment. Two heads, two fragments. And one of the key things here, when we communicate with the researchers, we always use this notation where this is the multi-head attention, and then with the parentheses of n is the number of head. So if you put 8 there, it means that it learns 8 idioms at the same time or 8 fragments at the same time. And the notation Q, K, and V means query, key, and value. Okay, in machine translation, query means target language or target sequence. K means the source language or the input. And V is the value, the things that you want to get from the drawer. Okay.
Hello, man.
Why am I mentioning this? So why did I spend so much time on this thing? It's because I want to focus on this. This is the key. If you use just only one layer of multi-head attention, you can learn idioms. If you use more than one layer, let's say 2 layers, you can learn idioms of idioms. What is idioms of idioms? It's a phrase structure. It now learns grammatical structure of a text. If you change the text into image, what's going to happen? It can learn the grammar of image, the composition of image. Let's say if you've got an image, it's composed of, let's say, sky, building, and in the building, you've got windows, and in the windows, you've got the frame, things like that. Can you see the structure? The whole thing, the whole picture And on the inside, you've got the sky on one here, and the other part is the building. And in the building, you've got windows. So you've got windows on the inside. And in the windows, you've got the frame. That can be learned with the transformer too. In the text, you've got phrase structure. In the image or video, you've got structure of image. It's exactly the same idea. And that can be learned automatically from the data. Here, in terms of transformer, we call this as encoding layer. Encoding layer means that when you use the multi-head attention, you can extract the idiom. One encoding layer, one idiom, or maybe more than one idiom, but that's one layer. If you use two encoding layers, you can extract idioms of idioms. If you use three, you've got idioms of idioms of idioms, and so on. It looks like this. If you put the input text in, and with the multi-head attention, you can learn 2 layers of idioms. That is one language. Now let's envisage 2 languages. What's going to happen? If we can learn the structures, the grammatical structures of 2 languages, let's say English and Thai, up here. Let's assume it has learned the structure of English and Thai. What's going to happen? Why don't we just feed the output of the multi-head attention of the source and the target into another multi-head attention? What's going to happen? If you feed the output into it, this is what it can learn. It learns to decode. Decode means translation. It learns to translate one idiom into another automatically. Let's say, if you put one layer of decoding into this one, it can now learn to extract looks up into search, and also some other words. That can be learned automatically. That is one decoding layer. What if we use 2 decoding layers? We can extract even more, like this word into this word. That can also be learned automatically too. If you use 3 layers, you can have even more, like look this word up as one phrase. That can be learned. And in this picture, this is how we train it. You may get a little bit puzzled, okay? In training the transformer, we have to shift the output for one word always. Because as I aforementioned in the beginning, we want to translate one word after another. So when you treat it, if you look at the first word of the target language, let's say Thai. So you've got marry, and then you translate into search. So it's the first and then the second. And if you give the second, like search, you get the third word, things like that. So therefore, when you train it, it will be right shifted. The output of the model will be right shifted. This is how it works. I mean, for the programmers, they have to learn that. For us, linguists, we don't have to. Okay, this is about implementation. So the transformer works like this. Okay, I've got about 45 minutes. Okay, 45 minutes. Okay, I'm so considerate of time. Okay, เกรงใจ considerate. Okay, so this is how it works. Okay, the model is given 2 input sequences, one in the source and one in the target. It could be anything. Okay, it could be anything. It could be the sequence of image, like sequence of fragments, or it could be sequence of words, or it could be a sequence of documents. This is how it works. And also the output. The output could be anything. just be a sequence. Okay. And then the input sequence will be fed into encoding layers. The encoding layers learns the structure automatically. It learns the grammatical structure of the input. If you have n layers, it means that your tree can be as deep as n layers or n depth. The first part is about extracting the phrase structures in the source. And you do the same thing in the target. Okay. The first part of the second thing is the extraction of the phrase structure in the target language. But the second part, the right part, is the alignment. It learns the correspondence between the structure of the input and the structure of the output, and it tries to map them together. So that's why we've got two sides. The first side is for phrase structure of the output, and the right side is about alignment, aligning the phrase structure of the input and the output. And then the result will be right shifted. This is deep learning. Very simple, right? In a nutshell, it's very simple. In implementation, it's fucking hard. Oh yeah, I'm not kidding. I'm using my swear words because it's really, really hard. And if you're wondering about some of these notations like position encoding, that means we put the index of each word or each, the index of each word or each fragment in the sequence, we also put that in, and that will also be learned too. Why? Why do we need to care about the position? It's because it will be used for penalizing. If it's too far apart, if it's, let's say, if this word and that word is about 100 words apart, you have to neglect that. You have to omit that already because it's too far apart. But if it's like 10 words apart, you may have to take that into account because it's close. That's why we have to care about the position. And we put the position encoding into the vector. If you're interested in this part, I can elaborate that. But given the time, I've got about 40 minutes. So I've got to be speedy. Okay. Or this is how I memorize the transformer. Okay. The transformer consists of 3 parts or 3 steps. The first one is encode. Encode means that it learns the phrase structure of the input. The second step is decode. Decode means that it aligns the phrase structure of the input with the output. That's decoding, mapping the correspondence between 2 idioms in the 2 languages. And the last one, produce. It learns from the state, the current state, and it produces 1 output words at the time. And I would like to also mention this part, not in this slide. Okay. In the real thing, in practice, we don't train the transformer by forcing it to generate 1 word at a time. We don't do that. We'll see that in a minute. That would be much more efficient way to do that. If you force it to work 1 word at a time, it's going to take forever to train. Okay. And this is the blue score. Blue score, or I'm not going to say it's blue score. If it's French, it's blur score. Blur. It's like, just like that. That's how French speaks. Yeah. Okay. Blue score is the score for evaluating a machine translation system. It basically maps n-grams, the similarity of n-grams. Like if you care about 1 gram or 1 word, that's unigram. So you count, okay, how many words, how many 1 words in the candidate can be mapped into the reference translation. And then you count that. and then you compute the score. If you care about bigram or 2 words, then you count 2 consecutive words, and then you count the similarity with respect to the reference. And then 3 words, so trigram. And then you compute the blue score by computing the geometric mean of the blue score of unigram, bigram, and trigram. It could be up to 5 grams if you are very strict. You can do that too. Okay, and also there is another metric, evaluation metric for machine translation. We call it rouge score. Rouge, it's not rogue, okay? It's rouge. It's red in French. So you've got bleu, which is blue, and you've got rouge, which is red. So blue and red. That's French flag. Okay. So the rouge score is now the recall. It's the ratio between the match n-gram against the reference. And you've got another one, which is rouge L. Rouge L means the ratio of the longest common subsequence of the between the reference and the candidate. So you can compute that. So there are 2 evaluation metrics for machine translation. For the third part of this these slides, I've got to skip because it's all mathematical. Okay, it's very mathematical. But if you're interested, you can find that in the slide and then read it. But unfortunately, I don't have enough time to explain that. So let's skip to BERT. Okay, I've got half an hour. Okay, BERT. What is BERT? BERT is a pre-trained language model, and it is trained based on Wikipedia. So you train a transformer to extract grammatical structures of English by using the whole Wikipedia and also books corpus. That's about 800 megabytes of mega words, and also Wikipedia. That's about 2 million words. I mean, no. It's about 2 billion words. 2 billion. That's quite large. And they set the configuration of the transformer as follows. So you've got the encoding layers. You've got about 12 layers. So Google assumed that the deepest grammatical structure is 12. Just 12, just that. As a linguist, we would say, no, it's not enough. But Google say, fuck it. I don't care much about it. Yeah. Okay. And also the attention head, they assume that there will be 12 idioms to be learned at the same time at each layer. Okay, 12 idioms or 12 multi-word expressions. And also they also set the size of the vectors. They set the size of the vectors as 768. Yeah. And also the number of parameters. Oh, this is the key. The number of parameters is the total number of the weight connection in the neural network. So they count that too. They count the number of connections, and they have 2 models, 2 base model, BERT base and BERT large. BERT large means very large. That's about 300 million connections. Very, very large. And as always, I have to mention how to train BERT. Okay. Most of the time, you would put the source language in and the target language out. That's how it works. But it doesn't stop there. BERT can be trained with multiple data sets, all of which unrelated to each other. As long as they are sequences, that's fine. The first task they use is machine translation. The machine translation, you've got the source language and the target language in the parallel text. So you put that in, and then you train the transformer accordingly. But you can also train the BERT with question answering system. You've got question, you've got answer. So right here, think about a Wikipedia entry. You've got an article in Wikipedia. You put the entire article of Wikipedia in. And then you annotate that with a question. Like you've got an article about Bangkok, and then you ask a question like, when was Bangkok established? You put that after the article. That will be the input sequence. And the output is the answer. Let's say Bangkok was established in 1726, things like that. So you put the output as the answer. How many questions, how many answers? You put that in, and then you train BERT. Easy, right? You can also train BERT with natural language inference. In natural language inference, you've got two sentences. The first one is the premise, and the second one is the entailment. Let's say the first sentence is, I slept like a baby last night. That's the first sentence. The second sentence, which is the entailment, could be, I snored so loud like a lion. So these two sentences are entailment because the first one must occur first before the second one occur. That's entailment. And this natural language inference can be used for training the transformer. Oh yeah. And the last one, abstractive summarization. If you've got a very large piece of news, and then you've got 3 bullets for the summary, you put the news at the input, and then you've got those 3 bullets as the output, and then you train the transformer. It can be trained like that too. So from the bird's eye view, you've got a task pool. Task pool means that you've got so many tasks you want to train the transformer with. So that's a task pool. And then you train, you put the input and the output, you map them, and then it can be learned automatically. That's a task pool. But once you finish the training, you can now stop and take those task pool out. What you really need is the knowledge encoded in the transformer. Because now it learns the grammatical structure, it learns reordering, it learns conceptualization. Therefore, you don't need the data anymore. You need the knowledge. You have extracted the knowledge, every drops of knowledge from the data, and then you throw the data away and then keep the transformer. And this model is called pre-trained model because it has been pre-trained either from Facebook, from Google, from Huawei, from any brand you can think of. They have their own data too. And once they finish the pre-training, they release the model. You can make use of that. Okay, I have mentioned this in the beginning. I'm going to mention this once again in details. This is how we train the transformer efficiently. Okay, this is how we do it. We've got the input sequence and we've got the output. Instead of forcing the transformer to generate the output one by one, no, we don't need that. We will use the game of guess instead. In French, we call it jeu de mots. Jeu de mots means that the joy of words. So you put a blank and then you guess the word, the missing words. That's jeu de mots in French. We are going to do the same thing in transformer. Okay, so here you've got the input as a sentence in English. Okay, but at this time, you put the mask on some of the words. Let's say 15% of the words, put the mask in, and let the transformer guess the missing words. If it makes the right guess, the loss will be 0. The loss of prediction will be zero. But if it makes a wrong guess, you compute the loss. Once you've got the loss, you can train it now. This is called mass language model, where you force the transformer to guess the missing words. Mass means that you put the mass on some words, and then you force the transformer to guess those missing words. Easy, right? Oh yeah, very easy. And this is the actual way of training the transformer mass language model. But we don't stop there. If we care just about one sentence, you can have the collocation inside the sentence. But what about entailment? Entailment can also be incorporated into the transformer as well. And this way of training is called next sentence prediction, or NSP. The next sentence prediction means that you put two sentences which are the entailment of each other. Like, I slept like a baby last night, and then I snore like a lion. So you put the two sentences, you concatenate them, and then put the mass and guess the missing words. By doing that, you're now forcing the semantic relatedness between each word of the two sentences. You mingle them, because if they are entailment, they must have some semantic relatedness or semantic relation. When you combine them as one's input sequence, those information can also be learned. Amazing. And in machine translation, sometimes the data set for machine translation can also be used for training a multi-language language model. It's now cross-lingual. For example, if you put the input in English in, you've got the input, the vector in input, the vector of English. But if you put Thai in the English transformer, you're gonna get anything. You weren't gonna get anything. But here, cross-lingual language model, whatever language you put in, you get the result. And those vectors correspond to each other too. Like the vector for the word big and yai, which means the same thing in Thai, they are very close to each other. That vectors can be learned. And this is how. Very, very easy. If you've got multiple languages in your data set, you take the two comparable sentences, you concatenate them. Like, this is the source and this is the target. You concatenate them, okay? As the input, right here, down here, that's English and French. Okay, you put English sentence and French sentence side by side. And then you do mass language model. You put some mass into the words, and then you ask the transformer to make the guess. By doing that, you're now sharing the information between English and French automatically. And this is called XLM, cross-lingual language model. It's very popular now. If you have more data, especially cross-lingual data, you can train XLM straight away. These are the main concepts. You've got mass language model, or MLM. You've got NSP, next sentence prediction, and the cross-lingual language model, XLM. These three notions will be used throughout the community of birds. In ACL, in the Conference of Computational Linguistics, we have an acronym for that. We call birdology. It's the science of bird and variants. Birdology. It's more like mimicry, okay? And people have asked these questions always. What kind of knowledge bird can learn? What does it have in here it has three kinds of knowledge. The first one is syntax or grammar. It learns the grammatical structure of the input and the output automatically. That's what you have seen in the beginning of the tutorial. The second one is semantic knowledge. It learns the semantic relatedness or the relatedness of meaning by guessing the missing words. It shares the information across the sentence or even across the language. That's semantic knowledge. And the last one, because BERT is also trained on books corpus and Wikipedia, some of the word knowledge can also be incorporated into BERT. Like people's name, or Bangkok was established in 1726, for example. That is incorporated in BERT. And as BERT was proposed in, I think is in 2018, many more BERTs showed up. Many more. I cannot elaborate all of them because it's going to take a whole day just to list them up. So I'm going to choose some popular variants for you, okay? I'm going to choose some. The first one is very popular. We call it Roberta, okay? Roberta is robustly optimized BERT, just Robert. Okay? Most of the time, it would be called Roberta or Roberta, things like that. Roberta is different from BERT. It's a little bit different from BERT, but it's much, much more robust. It means that it uses more stable vectors. It uses very close similarity to human, and this is why it's popular. Okay, the way we train Roberta is very simple. So remember the mask language model, MLM. You put the mask on some words and then you guess, right? In original BERT, we put those masks statically. So we replace each word in the data set, and then you make a guess. It will be marked statically into the data set. But in Roberta, no. It will be marked on the fly. So once you've got the input sentence, it will be randomly marked on the fly and then train the model. And you can feed the same sentence over and over again because the marks, the mask will be put randomly. You won't get the same mask. And here in Roberta, once they use dynamic masking, like I have aforementioned, they say NSP is not necessary anymore. So they don't need the entailment anymore. That's very good for some languages where natural language inference dataset is not available. But Thai, natural language inference for Thai is available. So therefore we can make use of that. Why not? And also the last one, they use larger dataset. So they incorporate books corpus and Wikipedia, and they also include news and web text. So it's very large now. So that's why Roberta is very popular. Although it was published in 2019, it's still used until today. The next one, which I really want to focus on, is the BERT, GPT, very popular, right? And BART. As we can see, as we have learned in the tutorial, BERT is about measuring the similarity across the input, right? So you measure the similarity between each word in the text, for example, or the similarity between each fragment in the image. That's BERT. But we also have a counterpart model. The counterpart model is GPT, Google pre-trained model. GPT, Google pre-trained model. Oh yeah, that's how they make up the acronym. Okay. The GPT works exactly different. I mean, completely different from BERT. it works in forward direction. So it predicts one word at a time. If you've got, for example, the sentence like A, B, C, D, the GPT will be trained to generate S to A to B, B to C, C to D, D to E, things like that. That is GPT. GPT is called autoregressive. Autoregressive means that once you generate the output, you take that output as an input and generate another output. That is autoregressive. Auto means self. Regressive means working on something. So you take the output of yourself and then work on something and produce another one. That is autoregressive. But BART, which is more modern way of teaching BERT, is like this. You can decompose the model into two parts. The first part is the BERT. That's encoding layer of BERT. In BART, you've got BERT for the encoder, and you've got decoder as GPT. So it's a mix between the two things. What it yields is more stability and robustness. It extracts the grammatical structure more robustly because it used the BERT. But at the same time, it generates a more meaningful output because it used GPT. So right here, if you're using the libraries like available libraries like FastSec or Google, I can't remember its name, you can train BERT, GPT, and BART using that library automatically. You didn't have to do much. You didn't have to do the coding anymore. Once you've got the data, you can train BERT, GPT, and BART. Okay, I've got, okay, 15 minutes. Okay, we can make it. Okay. The next model is Electra. Electra is a much more efficient BERT. It's even more efficient than Roberta, and it's very small. People start to look at Electra because it's very new. Okay, although it's not that new. 2020 is not that new anymore in terms of deep learning, because every model shows up every day, literally every day. So 2020 may be considered old already. Anyway, Electra. Electra is a more efficient and more robust model than Roberta. This is how we train it. Okay, it's very, very easy, but it has one limitation. Just only one limitation. Electra is used for classification only because it's discriminative. It is discriminative means that you cannot use it for as a generator. It cannot be used for generating sentences. Okay, so Electra is smaller, but it has one limitation. It's discriminative. This is how we train Electra. Suppose you have trained a BERT model, a very small one. Let's say very, very small one. Don't think about Google BERT. Okay, that's too large. Let's think about a very small one. Okay, you train that BERT, that small BERT, with the mass language model, just like the one that you have seen, guessing the words. And you use that BERT as a generator. Okay, it generates sentences. You use it as the input generator for Electra. And the Electra is trained this way. Okay, so you've got a sentence. That's the input sentence, like the chef cooked the meal. And you force the mass language model here to generate a sentence that looks almost like the input. But now, let's take a look. The output is the chef ate the meal. There's slight difference. Okay, the chef cooked the meal and the chef ate the meal. The Electra works this way. It will discriminate whether this input is a genuine one or a generated one. It will detect whether each word is the original one from there, or it is replaced mysteriously by the model. Oh yeah. And you train both model at the same time. This is how it's trained. It may look a little bit similar. It may ring your bell if you're working on image processing, because this is GAN. You've got a generator and discriminator. The generator, for example, generates fake photos or fake pictures. And the discriminator works as a policeman trying to catch the thief. If he's mocking a photo or mocking a picture, or is it the genuine picture? So you can adapt GAN into natural language processing in Electra by training Electra. See? Amazing, right? Amazing. It's not the end of the story yet. I'm finishing. Okay. I'm finishing. Okay. There are also two linguistic-based birds. Okay. The first one is span bird. The span bird means that you don't just mask one word. You now mask a chunk, a whole chunk, a phrase, and idioms, and you force bird to make a guess of the missing part. For example, you can mark the whole thing, the whole chunk, and then bird makes prediction, a football championship tournament, things like that. You mark the whole noun chunk, and you force bird to generate that. Why we have to do that? It's because you are now forcing bird to learn specific idioms. If you really want to force bird to incorporate specific idioms into it, you can now use span bird. And also struck bird. Struck bird is a little bit different. Okay, in struck bird, you deliberately or intentionally scramble the words, some words in the sentence, and then you ask bird to reorder it back to the original position. That can also be done. Struck birds make a guess for the right word order. Therefore, you're now forcing specific word orders or specific translation method into the model. The next one is T5. You may have heard the term T5 so many times. But T5 has nothing to do with machine translation at all. It has nothing to do. T5 means text-to-text transfer transformer. If you count the number of T, you've got 5T there. Text-to-text transfer transformer. 5T, therefore T5. Oh yeah. The idea of T5 is even simpler than you think. In here, the T5 can be trained by converting all data set into a singular format. A single format. It works that way. Let's take a look at the first one, machine translation. In training T5, you convert every sentence pair into translate English to German colon. That is good. And the output would be, das ist gut. I'm mimicking German manner. Das ist gut. Okay, so anyway, that's how we translate the data set for machine translation into text, okay? Because transformer is about transforming a sequence into another sequence. Therefore, you convert that into text. One single format rules them all. The next one is semantic similarity. You may say similarity, sentence 1, sentence 2. You put that in, and it learns automatically. That's the input, and the output is 3.8. That's the number of that's the similarity measured in numbers. The next one is summarization. You may say summarize colon, and then you put the whole text in, and then the output would be the summary. That's input and output. It's about the format. When you train a transformer model, you have to think about the format of the input and the output. It must be in the text or in the sequence. That's all. And the last one, which I don't mention, is cola sentence. Cola means collocation, whether these two sentences can collocate in the same text. You may say, cola sentence, colon, the chorus is jumping well. It's a little bit weird, right? And that sounds a little bit weird. And then up there, the output is not acceptable. So you can think about that. You can think about the output, I mean, the format for the input and the output. You can combine many data sets available in your repository and then train BERT. It could be anything now. It depends on your format. Okay, I've got 7 minutes, 7 fucking minutes. Okay. The next one is DistilBERT. DistilBERT is trained. Okay, let me focus this first. Okay, DistilBERT is a small bird. If you have a large bird, like very, very large one, you can train a smaller one, like much smaller, that works almost exactly the same as large bird by using the technique called knowledge distillation. Knowledge distillation is to train a smaller model. We call it student model. We train a student model by imitating what the large model does. We are going to force the student to imitate the teacher. How to do that? It's much simpler than you think. Okay, so you've got a teacher model, very large one, and you've got a student layer, which is very small one. Small, how small? If the teacher model has got 12 layers, 12 encoding layers, the student could have just 3 encoding layers. But it tries its best to imitate the teacher. Okay, so this is how we do it. We force the student to imitate the teacher by computing 2 kinds of loss. 2 kinds of loss. The first one is the loss of the hidden layer. You try very hard to force the internal of the student to work almost as if it's a teacher. So you compute the loss between the hidden states. And the next one, you compute the loss between the attention matrix, the one that you have seen in scale.product. You compute the difference between the 2 tables, and then you try to minimize the loss by using stochastic gradient descent. Just that. That's how it works. And now DistilBERT is also very popular when you want to deploy a pre-trained model onto small devices. Pre-trained model like DistilBERT is the key. And the last one, I spent 2 hours last night trying to understand the XLNet. And I'm afraid I'll try my best. Okay, I've got 4 minutes now to explain it. Okay, so the idea of XLNet is very close to transformer, but the main problem of the transformer is the input size. When you compute the scale.product, the similarity table, there this could be very large. If you have let's say 1,000 words at the input, the table would be 1,000 by 1,000. That's 1,000,000 cells in the table already. So it could be very large. Transformer XL was invented to circumvent this problem. So the idea is very simple. If you have a very long sequence, you break it down. into small chunks. It could be like four words. That's very small transformer. You take 4 words at a time, and then you compute the loss. When you train the transformer, you compute the loss of that chunk, and then you slide the window into the next 4 words. But these 4 words will have the information linked from the previous chunk as well, because it's the attention table. So it's a whole thing. When you compute it, you freeze the entire sequence except that 4 words, and then you compute the loss and just adjust the connection in this sliding window, and then you move the sliding window along the way. That's how you deal with a long sequence, and that is called Transformer XL. And because Transformer XL is based on sliding windows, sometimes it's very slow. The sliding window could move very slowly. So they also propose another thing called permutation language model. The permutation language model is actually the flexible bidirectional context information. So suppose you have 4 words, like 1, 2, 3, 4. You scramble the order. So you may get something like 1, 4, 2, 3. And then you treat the order of the permutation as the loss. Here, you've got 1, 4, 2, 3. So you first compute the loss for just only 1 word, x1. And then you move on to 4. You compute the loss for x4 given x1. So that's the information as you have already computed. And you pass through the permutation. That's how you compute the loss along the way. These are the birds that we have aforementioned. Allow me to conclude my talk. Okay. Fuck yes. Okay. Okay. So what we have learned today is the transformer model. The transformer model transforms a sequence into a sequence. The sequence could be anything. It could be image, it could be video, it could be text, it could be speech signal. It could be anything, as long as you can encode it as a sequence. And the transformer model works in 3 steps. Okay, it works in 3 steps. The first one is encoding. Encoding means that it learns the grammatical structure of the input sequence, and it also learns the same thing on the output. The next one is decoding. Decoding is to map the correspondence between the input sequence, the grammatical structures of the input sequence and those of the output sequence. And the last one is production, produce the output along the way. The way we train the transformer can be abridged into 3 steps, 3 things. The first one is mass language model, where you put the mass on some words randomly, and then you compute the loss of predictions on the missing words. That's mass language model. The next one is next sentence prediction, where you put 2 entailed sentences alongside each other, and then you do the mass language model to share the semantic relatedness between words. And the last one, XLM, cross-lingual language model, you put the comparable text. It needs not be translation, okay? They just need to be comparable. So you put 2 comparable texts alongside each other, and then you do the mass language model to share the information across languages. That is 3 notions of the bird right now. And that summarized my talk. Thank you very much. Would you like to ask any questions? It's already coffee break, but we can have a short coffee break if you want to. Yeah. You can ask a lot of questions. Yes, please. Here we go.
Thank you. So could you go back to the slides where you you were describing the computation of the dot product attention
Right.
matrices. So in your table, there were like the value columns, what I didn't understand fully. So what did the triangle shape and the heart shape represent in this case?
Oh, it represents a vector. It could be a vector of the word like Mary, looks, or it could be some other kinds of vector or representation. As of today, I represent each shape with the vector, but in the future, it could be qubit. It could be quantum bit too. So right now, yeah, it's a vector first.
I see. So the combined results is basically the weighted combination
Exactly.
of the vectors.
Exactly.
I see. Okay. Thank you.
Thank you. Yes, please.
Ajahn, I would like to ask you that as we are a teacher, sometimes we ask our students to write some essay, and I understand that some of our students use tools
Exactly.
to create their essay, and I'm stuck that how I'm going to deal with this kind of uses of this NLP technology. Please suggest me. Thank you.
Okay. This problem has also been a concern of many language teachers today. I went to KMUTT, King Mongkut University, Thonburi, and some of the lecturers in the Department of English actually complained about the use of language model in writing an essay. They have the same problem even in Bangkok. So this is how they solve the problem. This is how they solve the problem. I'm not saying it's recommended, but this is how they do it. So they ask the students to come to the exam room and write it down on the sheet of paper. They could have as many resources as they like, dictionary and stuff like that. They can do that, but they have to write on the sheet of paper with no computers. And I asked them why. Why did you force your student to do that? They say, this is the way human learns. Human learns by muscle memory. I'm not kidding. They learn by muscle memory. They need to write it down so that they can remember. Just like the way we go to the lecture, if we type that in, it's not going to stick into your head for so long. But if you write it down, it's going to stay there almost forever. So they force their students, especially in writing classes, to write it down on the sheet of paper instead of submitting on Google Class. Or if they use Google Classroom, they need to write it down on paper and scan it so that they can mark it. So this is how they solve the problem. I'm not saying that I'm recommending this solution. It may be a good idea, but to me, it's not really. Yeah. Yep. Any questions? Yes, please. Oops. เกือบลงมาไม่ทัน
In terms of sign language, so we can use this approach to apply the sign language to translate from gesture to any other language.
Definitely.
Okay.
Definitely. And yeah, please go ahead.
Please recommend the best model for this approach too.
Okay. I think one thing is that sign language interpretation is about translating gestures into text, right? And the gestures, I think there is a standardized way of encoding a gesture into text, as I aforementioned, that's the best of my understanding. And if you can encode the sign language into textual representation, then you can use the transformer straight away. But the problem is about interpretation, where you've got the gesture like that, and then you have to use, I think you have to do the video processing to translate that into the textual representation. I think the main contribution would be there. So it depends on your data too. If you have a lot of data, you can do that. Oh yeah, and at the moment, there is also a transformer. We call it a video transformer, where you've got the I think you segment the video into chunk, and then you pass that into the transformer straight away, and then it learns the collocation of the gesture and the text. That can also be learned automatically. I think that's video transformer. Yeah. Actually, Professor Samparit is just there. He's an expert of video transformer. That's him. Yeah. That's him, right? That's him. Okay, any questions? Oh, okay, we've got one question from the chat. Okay, let's take a look at the chat. Let's see. Okay, let's go to the chat. And what would be the question? Okay, the first question is from Mia Aisan. May I know where I can download the PowerPoint? Oh, okay. I think it's already up there. Let me repeat that over again. It's already up there. Okay, and the next question is, I want to create a system that can generate a new long article based on a given topic. Oh yeah, that's a very good question. Okay, which has the content that is unique to other articles already available on the internet? Which model should I choose? Okay, this is a very interesting question. I would recommend BART. For this question, I would recommend BART. BART is a combination of BERT and GPT. BERT is very good for extracting grammatical structure in the input. And GPT is very efficient in generating new text. Even the pre-trained language model that we have mentioned in the writing classes, these models are based on GPT. It generates the text as if it's a human. So close, but it's actually imitating how human write. It's just that, because it remembers the phrases, remember how the writing style would go, how to use the words, things like that. So GPT would be the key here. If you want to generate a new article, new long article from a given topic, I think GPT would be the key. No, I mean BART, but BART is not so widely available. So at this point, I would recommend GPT. GPT is available in many languages like English or Thai or Myanmar. So yeah, I think that would be beneficial. Okay. Mia-san, she's got a very, very good question. Okay. May I know the best way to improve the performance of the pre-trained models in machine translation tasks? I mean, by varying batch size or tuning hyperparameters. That is a very, very clever question. Okay, how to improve the downstream model? Okay, in Bertology, we don't actually adjust the pre-trained model because it's been learned from a very large data set. But we can work on our model, which we call downstream model or downstream task, like machine translation. How could we do that? Yeah, so my recommendation would be varying the batch size. Yeah, that's the first thing. That's the number of input you can put into the training. And you have to experiment a lot more because batch size is very sensitive. I tried that, and different batch sizes yield different results, completely different results. And also, you may have to think about the size of hidden vectors. The size of hidden vectors, especially from the pre-trained model, play an important role. It plays an important role in the accuracy. So think about it very quick. Think about it very thoroughly. Tuning the parameters. Yeah, that may be the case too. At the moment, we use Atom. It's not Adam, okay? Yeah, and what Adam is Atom. So you use Atom optimizer. But as of today, we don't use Atom anymore. We use Atom W, which is an improvement version of Atom. So you may try Atom W as well. I think it's available on PyTorch and Keras. So you may want to try it. Okay. Okay. Any questions from the audience as well? Okay, not yet. Yes, please. รับไมค์ไหมคะ ครับอาจารย์ครับเขาได้ครับครับ
Okay, I have
Last
a question. I have a questions about BART model.
Okay.
It seems that BART model is composed of encoder and decoder, so it's just the same as the original transformer, right?
Right.
Or the question is, I'm not sure why we what is the new improvement of BART model?
What is the improvement of BART? That is a very good question. So BART is a combination of BERT encoders layer and also the GPT decoding layer. So that is the key. So one drawback of the BERT is that it generates the output sentence not so naturally compared to GPT, because GPT also is autoregressive. Therefore, it takes into account the previous output and it generates the next output. But here in BERT, you take care of the whole thing. Therefore, you may be distorted.
Okay,
You may be distracted by the context.
a little more question.
Yeah, sure. Yeah.
About how do we use the feature vector provided by the encoder inside the GPT? If it were transformer, we use cross attention, right?
Exactly.
And in BART, I'm not sure. Do we do that, or we just concatenate with the text input and then decode?
I think that I think the last one that you mentioned would be the method. I haven't taken a look. I mean in details, but I would envisage concatenating the output vectors from the BERT and then put that as an input for the autoregressive model in BART.
Thank you.
Yeah, I would do that. Any other question? I'm mimicking SpongeBob. You know SpongeBob SquarePants? Yeah. Patrick. Okay. So no more questions. So thank you very much for coming, and I'll see you in the conference. Just catch me up. Okay. Catch me if you can. Okay. Thank you very much. Bye.